Yeah, hello there and welcome to our evening lesson. We have been looking at energy and forms of energy specifically, whereby we said that energy is actually the ability to do work. It is actually the ability to do work. Now, different forms of energy, like we previously discussed, can bring about different abilities to perform different tasks as desired. Now, remember that the task that you perform using a form of energy is going to be informed even by the tools and the machine that you pick on. Now, today I want us to narrow down to heat as a form of energy. Heat as a form of energy and see what heat can do for us. Now, before we continue, it is good to ask ourselves, what is this heat that we are talking about? Now, heat is actually a form of energy Now, heat is actually a form of energy to start with, and this form of energy flows from one body or from one point to another because of temperature difference. Now, what is this temperature then that we are talking about? Now, temperature in itself is the degree of coldness or hotness of a body. Actually, it is the degree of coldness or hotness of a body. Is the degree of coldness or even hotness of a body. Now, for example, when you get hold of a hot piece of metal, you withdraw your hand because that particular body is hot. In other words, its temperatures are high. Now, that degree of coldness or hotness is what we call the temperature. Now, that one is what brings about the flow of our form of energy of interest, which is heat. Now, it is important to point out that heat flows from a body of high temperatures. For example, we could have two bodies here, where one is at 100 degrees centigrade, for example. The other one could be at 20 degrees centigrade. Now, we expect that the body at higher temperature is going to give out some heat to our second body, which is at a lower temperature, and therefore the flow of heat will be from our body A to B. Now, that one is brought about by that difference in temperatures. Now, there are a few things that we expect will come about when heat flows. Number one is that a body could reduce or increase its temperatures. A body could increase or even reduce its temperature. Now take for example the two bodies that we have considered. Call this one A and this one is B. Now A is at a higher temperatures, that is 100 degrees centigrade, and B subsequently has a lower temperature. Therefore we are saying that heat will flow from A to B. Now what will happen is that temperature of body A is going to reduce because it has given out some heat, and the temperature of B is going to rise in relation to the amount of heat that it absorbs from body A. Now when a balance is achieved, now you expect the temperature of the two to have balanced. They will at the end of the process have the same temperature, meaning A will have reduced its temperature while B will have its temperatures raised. Now, number two, you could also achieve a change of state. Now, here, remember that we have matter existing in three states. That is, we have a solid, we have a liquid, we have the gaseous state. Sometimes we can also add what we call plasma. Plasma is a minor state of matter where some molecules exist as ions. While others will exist as a gas. Now, depending on the amount of heat that matter receives, it could transform from a solid to a liquid, for example, or even to a gas. It could vaporize. Alternatively, if the body has lost its temperature, it could go through the reverse of the processes, where now we can have a gas changing to a liquid or even subliming to a solid. Now, number three, you could also have some work being done. By virtue of a body having received heat. Remember that heat is a form of energy, and therefore, being a form of energy in itself, it has the potential to do some work, because energy is the ability to do work. Therefore, if you have a body absorbing some heat, it could result in some work being done. Now, let us look at modes of heat transfer. Modes of heat transfer. Now, modes of heat transfer are simply the ways through which heat can be transferred from one body to another, be it a solid, be it a liquid, or even a gas. Now, basically, we have three modes, and one of them is conduction. We have convection and radiation. We have the three. We have conduction, convection, and radiation. Now, depending on the bodies that are exchanging heat, you could involve any one of the processes like we are about to discuss. Conduction is mainly heat flow through solids. It is actually heat transfer or heat flow through solids. What we mean is that we will have a solid at a higher temperature, another one at a lower temperature, and when heat is exchanged between the two bodies, like in our previous example, the process involved is called radiation. Now, radiation happens mainly through vibration of particles in the medium. So what we are saying is that for conduction to take place, a medium is paramount. A medium is paramount because the vibration of particles in that medium is what is going to bring about conduction. That is the flow of heat through the solids. Now, which particles are we talking about? You could have molecules, or even free electrons. You could have molecules or even free electrons. Therefore, conduction in itself, when it is taking place, the whole body need not move, because what we are interested in is the motion of the particles that compose of the solid. That one could be either molecules, free electrons, or even atoms in the medium, or even atoms in the medium. Now, based on the fact that the vibration of particles is what is going to inform our process of conduction. Now, we could have materials being classified now based on how well or they conduct heat. They could be either conductors, they could be poor conductors, or we could even talk about insulators. Materials could be conductors, poor conductors, or even insulators. Now, conductors contain a high number of free particles. For example, metals will contain a high number of free electrons, and atoms. That is why we classify them as good conductors. Now, as you go down, the conduction gradient is going to reduce, because now poor conductors will have fewer particles to conduct heat, and the same case applies to insulators. However, we could even talk about the spaces between the particles, or even the bonds with which the particles are held together. They also have a take in as far as conduction of materials is concerned. Now, let us think about factors affecting conduction. Factors affecting conduction. Factors affecting conduction of heat. And basically we have 4 factors affecting conduction. Number 1 is what we call the temperature. Difference. We could call it delta theta. Now, the temperature difference is responsible for setting the gradient of flow of heat. Now, the greater the difference in temperature, the steeper the gradient is going to be, and subsequently conduction is going to be faster. Therefore, we say that the higher the temperature, difference, the higher the rate of heat flow. The higher the temperature difference, the higher the rate of heat flow we are going to achieve, because the gradient is going to be steep. We could also look at another factor, and that is the length of a conductor. The length of a conductor. And here you understand, or you realize, that heat flow is through some imaginary lines which we are going to call lines of heat flow. Lines of heat flow. Now, these imaginary lines are found in conductors. Now, these lines of heat flow diverge from the point of heat source, like so. Now, these are what we call the lines of heat flow. Now, these are lines of heat flow. We are assuming that at this point, this is where we have a source of heat hitting one of the ends of our conductor, and the heat is taken up by these lines, and through them we have the distribution of heat throughout the conductor. Now, from our diagram, you can be able to see that the nearer the point of the conductor is to the point of heat source, the more the lines of heat flow we are going to have crossing that particular point. That nearer to the source of heat, we have so many lines of heat flow, and they reduce as we advance to the end of the conductor. Now, that is to mean that at this point that is close to the source, we are going to have a lot of heat being distributed as opposed to the areas which are at the far end of our conductor. And for that reason, the shorter the conductor, the higher the level, or the higher the rate of heat flow. The shorter the conductor, the higher the rate of heat flow. The higher the rate of heat flow. Now, on to our factor number 3. On to our factor number 3, which we are going to call cross-section area. And here, I want us to take an example of a solid, say metal, and we take some two conductors. One is going to have a big cross-section area, and the other one has a smaller cross-section area, but the same length. Now, we put a source of heat here, and equally we put another one here. We agreed that heat flow is by vibration of particles. Now, at this cross-section area, you are going to have electrons that are free to conduct heat all over the cross-section area. Now, this other area is also going to have its own fair share of electrons. Now, clearly, we can be able to establish that the bigger the cross-section area, the higher the number of free electrons we are going to have. All these electrons will be responsible for the flow of heat throughout the conductor, and the same case will apply to our second conductor. Therefore, the bigger the cross-section area, the faster the rate of heat flow. The bigger the cross-section area, the higher the rate of heat flow. The higher the rate of heat flow. Now, number 4 is the type of material. Type of material is our fourth and our last factor affecting conduction. Now, what about it? Now, the type of material determines the amount or the number of free particles in that particular material. One material will have fewer particles than another one. Again, that is the first aspect, number of free particles. You could also talk about the bonds holding particles together. The bonds holding particles together. In one material, they could be stronger than others. In one material, the bonds could be stronger than others. And for that reason, we say, depending on the type of material, we are going to have different rates of heat flow because the two factors have to be taken into consideration. Let us say something about convection. Convection. And convection is basically heat flow through fluids. It's actually heat flow through fluids. And fluids, we pointed out that fluids include liquids and gases. Liquids and gases. Now, heat flow through these two, which act as medium of heat flow, is what we call convection. Now, as opposed to the case we've had with conduction, we have realized that for conduction to take place, the medium need not move, because what we are interested in is how vigorous the vibrations of particles in that medium is going to be. Now, in this case, the fluid itself has to flow. Now, the fluid flows, setting up what we call convection currents. Convection currents. Now, in this case, whether the particles are moving or not, we will want to have our fluid literally moving from one point to the other. But now we agreed that fluids take the shape of the container in which they are put, and for that reason we talk about them moving in currents. They cannot literally move because they have to be in a container. They have to set a convection current, which is going to be informed by some factors which we are just about to look into. Let us take an example of water. We want to heat some water. We want to heat some water in a container. Let us put our source of heat at this point. Our source of heat. And this is water. Now, what happens? Water is a bad conductor of heat. Therefore, when you heat this place, you do not expect the heat to be conducted to other parts of the water. What will happen here is that the water will expand. When heated, water expands. Water expands. And the expansion at this point, but not in the whole container, we are only interested in the point that it receives heat directly. Now, at this part, when you heat this part, water at this part is the one that is going to expand. Now, subsequently, volume increase and density decrease. At this point, volume of the water increases while its density decreases. Now, remember, at these other parts, we have water at its original state because it has not received heat. So what will happen to this water is that it's going to rise up, and some cold water at lower volume and higher density is going to replace it. So once again, we get to this point. The same process is repeated. Water is heated, leading to an expansion that subsequently increases its volume and reduces its density. So the water continues to rise, and more cold water is going to replace it. Now, that process is continuous until all the water in the container is heated to the same level of hotness. Now, you could leave your container like that so that the water in itself goes through the process on its own independently, or you could decide to aid the process by stirring. Now that brings us to the types of convection. Types of convection. Number one is what we call natural convection. A natural convection is where you let the process of convection to take place independently. Here, the process of convection is left to take place independently. Is left to take place independently. That is why we are calling it natural. However, you could have another one which we call aided convection. Aided, or what we call artificial convection. And this is where you decide to aid the process by stirring. Here, the process of convection is speeded up through stirring, external stirring. Now, let us talk about radiation, which is our last mode of heat transfer. And radiation in itself is where heat flows through radiations. Like, for example, from space, where we have a vacuum, we don't have a medium of transformation of heat. We get the heat from the sun, for example, through radiations. So now, where we don't have a medium, we say that heat flows through a vacuum, through a vacuum. Here, by vacuum we mean that no medium is needed. And we have already given the example of heat from the sun, that we are not going to require any medium, no vibration, no movement, it's simply radiations. Now, having looked at the three modes of heat transfer, now we qualify to go a notch higher and probably look at heat capacity. Heat capacity. Heat capacity. And heat capacity, now when we are talking about heat capacity, we look at the body that is receiving heat wholesomely. We look at it wholesomely, and we say that heat capacity is that amount of heat that is needed to raise the temperature of a given mass of a material by 1 degree centigrade or even 1 Kelvin. The body is taken wholesomely, its mass is considered as a unit, and therefore heat capacity is therefore the amount of heat energy needed or required to raise the temperature of a body that amount of heat energy. Remember, we said that heat itself is a form of energy, but it has to flow where we have a temperature difference. So the two ideas are actually intertwined. You cannot separate them. Now, that amount of heat energy that you are going to require to raise some mass of a body by only 1 degree centigrade or even 1 Kelvin is what we call heat capacity. Now, numerically, heat capacity, which we are going to symbolize by capital C, is given by amount of heat we are going to call it Q, and we divide this by mass, or the temperature change. Temperature change. That our heat capacity is going to be given by amount of heat divided by change in temperature, which we are going to call delta theta. Therefore, C in the uppercase is given by Q over change in temperatures. Q over change in temperature. C, our heat capacity, amount of energy required to raise or the temperature of a mass by 1 degree. This is the energy at our disposal, and this is the change in temperature that results thereof. Now, let us take an example. Now, before we look at the example, it is good that we point out the units of our heat capacity. Now, heat is energy, and energy is measured in joules. And now, temperature is measured in Kelvin. Kelvin, we have the Kelvin scale to measure the temperature. Therefore, what we are doing in essence, we are dividing joules by Kelvin, and therefore our units becomes joules per Kelvin. Heat capacity is given by the amount of energy divided by the change in temperature, and we measure it in joules per Kelvin. Now, back to our question. The question reads that calculate the amount of heat required to raise the temperature of a metal block with a heat capacity of 460 joules per Kelvin from 15 to 45 degrees. Let us go back to our formula and look at what we have been given. We have the heat capacity as 460 joules per Kelvin from the question. We also have a change in temperature being equal to 45 minus 15, which gives 30 degrees Celsius, or Kelvin if you may. Then we are interested in the amount of heat. We are actually interested in the amount of heat, and here we say but heat capacity is given by the amount of energy we have. This one we divided by change in temperature. That heat capacity is given by the amount of energy, and this one we divide by change in temperature. Let us put in the values of our variables because we have them from the question, and that way we can go to the unknown working from the known. Now we have our C being equal to 460 joules per Kelvin, and this one will result from the amount of energy that we have divided by our change in temperatures, which is 30 degrees Celsius. Now, making Q the subject of the formula here, we will have Q being equal to C times delta beta. That Q, which is our energy, is given by heat capacity multiplied by change in temperature, and from our what we have, this one will be given by 460 joules per Kelvin, and this one we multiply by 30 degrees centigrade, and what we get here is 13,800. 13,800. What are the units? Ask yourself. What is heat? It's a form of energy. Therefore, we are justified to take the units of energy to measure our heat, and therefore it is going to be joules. Joules. 13,800 joules. That is what we shall have. Now, we could also look at another example. Example 2. we have yet another example, and it reads, a piece of metal of mass 4 kg is heated so that its temperature rises from 21 degrees centigrade to 47.5. Now, the question requires us to calculate the amount of heat that is absorbed by the piece of metal. Now, from the question, mass is 4 kgs. Now, the temperatures rises from 40 to 47.5 from 21, which is given by, which gives us 26.5 degrees Celsius, and we assume the specific heat capacity or the heat capacity, we assume to be 460 joules per Kelvin. Because it's a piece of metal, it's a second part of the first one, so we assume the heat capacity is similar. Now, but we know that heat capacity is given by amount of energy divided by change in temperatures. Amount of energy given divided by change in temperature, and here of our interest is the amount of energy, implying that Q is going to be C times delta theta, which gives us 460 joules per Kelvin. We multiply by 26.5, and this gives us 12,190 joules. Now, kindly remember that every time you are required to work out, unless the question requires you to work out the specific heat capacity, if you are to use it in your calculation, it is always going to be provided. Therefore, do not memorize. Questions that do not give you the specific heat capacity will give you the parameters that are needed so that you can calculate it yourself. But otherwise, it's always going to be provided. Now, that's about all for the introductory bit on heat. Next time we meet, we are going to discuss specific heat capacity and even expound more on how heat can transform or change the states of matter. Until then, I wish you well. Thank you.